Hello everyone. So today we're going to discuss about relativity, under which today our topic will be more on reference frames and understanding of Lorentz transformation equations. So let's start with what do you mean by the term frames? Like, I mean, basically when I say frames, in a sense, reference frame. Like if you observed or not, or if you recall the topics that we have learned under A1, A2, or A3 about the mechanics, we used to talk about the object is moving with constant speed, the object is moving with some acceleration, right? So it was all with respect to a reference. For example, if I'm saying that, I'm moving in a car with a speed of 70 kilometers per hour, with respect to what? With respect to the ground, because the ground is at rest. Or another example, let's say there are two cars, both are moving at the same speed. Car one with speed 80 kmph, car two also with speed 80 kmph, then obviously they both will be at rest with respect to each other because both are moving with the same speed. So basically, what I meant to say is like, I mean, while we talk about speed, a motion, or giving a coordinate, giving a position to something, it is all with respect to some reference. So that is what we are talking about today, about reference frame, right? But in this, generally, when I talk about a coordinate, let's say I'm talking about where you're sitting right now in your room. Definitely, you're going to consider your room as a three-dimensional space, right? So your height of the room is going to be a y-axis, your length of the room, if it is x-axis, and your width of the room is z-axis, right? And if I'm asking you, what is the coordinate of you sitting? Maybe you're sitting in this position here, right? So what is the coordinate of your position here? So you're going to tell how far you are along the x-axis, how high you are along y-axis, and how far you are along z-axis. That's going to give you your coordinate, right? X comma y comma z. In addition to that, what Einstein has said that there is a time coordinate to it, which is given a fourth dimension to your position. So basically, meant to say that your x comma y comma z may not be same all the time because you might be moving. So your coordinate of x comma y comma z is restricted to a given time, and therefore your x may change with the change in time. That means there is a fourth coordinate added to it, and I'm going to call that as a time coordinate. And therefore, this makes it a fourth dimension, right? It adds a fourth dimension to your space. And that's why we call it as space-time, right? We call it as space-time. Now, each and every point has its coordinate axis and along with the clocks assigned to it. Let me call this, let's say this coordinate A is x1, comma y1, comma z1 with a time t1. Similarly, there's another point B with x2, comma y2, comma z2 and along with the time t2. So that means each and every point in the space has its own coordinate along with the clocks. And we call this as a reference frame. Okay, this entire set of coordinates along with its time is what we call it as frame of reference or reference frame. Yeah, so let me read out the definition. A reference frame is a set of coordinates that can be used to determine the positions and the velocities of the object in that frame, right? Or it can also be defined as a reference frame is a set of coordinate axes, which is basically x comma y comma z, and a set of clocks at every point in space. Clear? Now, when I'm talking about coordinate axis, you must have seen I'm talking about the three-dimensional axis, right? I mean x comma y comma z, but in this whole unit, we're going to consider only two-dimensional space. We're going to ignore the third dimension, which is z-axis. So we're going to consider x comma y along with the clocks, which is time period. Now, because we're talking about reference frame, we have to also understand about the types of reference frame we have. Okay, so we have two types of reference frame. One is called inertial frame of reference, and second one is called as non-inertial frame of reference. So what is inertial frame of reference? Inertial frame of reference is where the object is not experiencing any external force. So there is no external force acting on the body. Therefore, the net acceleration of the body is zero. What does it mean? That means the body which is at rest will stay at rest, and the body which is in motion will continue to move with a constant speed. Very simple. That's why Newton's laws of motions are applied here. That's what one of the lines says, the Newton's law holds true here. But where is non-inertial frame of reference? In this case, the net force acting on the body may be zero, okay, may be zero, but the object may accelerate. Okay, I mean, what do you mean by that, sir? Let's take an example. As you can see this picture over here, there is a cart which is accelerating with acceleration A, and you can see there is a pendulum bob which might be initially at this position here, which has been deflected by an angle theta. So who is pushing this pendulum bob here? So there is a pushing force, but in reality, that doesn't exist. It is a frictious force, right? It is an imaginary force that is pushing the pendulum back, and that force is called as pseudo force. Clear? So what is a pseudo force? It's basically called, sorry, pseudo force, Pseudo, pseudo force. That's basically means imaginary force or fictitious force. So as you can see that Newton's laws doesn't include pseudo force in any of the discussion. Maybe Newton's first law of motion, Newton's second law of motion. We never bring pseudo force into the discussion, correct? But I mean, you can see there is no net force acting on the body for body to make it move. But still it's accelerating because it's accelerating backward. Or take another example, like you're sitting in the car started, I mean, car is moving with constant speed, you will neither fall forward nor you move backward. But instead, if you're accelerating, then you know that your body will going to move back and you feel like someone is pushing you back. So who is that someone pushing? There's no force acting on you actually. So that means, but you're accelerating backward, right? You're accelerating backward. It's all because there is a pseudo force acting on you. Now you say, sir, so what is pseudo force? I know there is no force acting on you, but it's all due to the inertia that you're moving back. But since that acceleration must be due to some force, and we named it as pseudo force, and therefore this pseudo force makes the entire calculation very complex and makes it difficult for us to solve a situation. And that's what we say that Newton's law does not hold true in these frames. Which frames? Non-inertial frame of reference, in which the object is accelerating. And when I say object is accelerating, I don't mean to say one of the object in the given frame. It all basically means the entire frame is accelerating. Okay, fine. So I repeat once again. Types of frame of reference. We have two types: inertial frame of reference, non-inertial frame of reference. What is inertial frame of reference? It's where the acceleration is zero, and non-inertial frame of reference where the acceleration is not zero. And one of the example is like you're moving, you're moving in a car. Suddenly, I'm assuming your car is a reference. Okay, your entire car is a reference, and you are one of the object inside that reference. And because your reference is accelerating, you are also accelerating, but you're not being accelerated by any force, and therefore we name that force as pseudo force. And since I can't explain what is a force, I can't calculate the force there. Therefore, Newton's laws does not hold true in that frame. Hence, non-inertial frame of reference uh, we don't use it. I meant to say that this entire unit we don't talk about, or not even this unit. I'm talking about relativity. When we talk about relativity, we only consider the inertial frame of reference because only there the Newton's laws holds true. Okay, so keep that in mind. Now, so let's talk about this question here. Which reference frames in this listed are inertial frame of reference? So when you answer this, remember that a frame of reference where the particles accelerate, it's called non-inertial, and a frame of reference where the particle do not accelerate is called as inertial frame. So skydiver falling freely, obviously it's accelerating, hence not an inertial frame. Skydiver falling at terminal velocity means acceleration zero, therefore yes, inertial frame. A train moving at constant speed, yes. Plane taking off, it's accelerating, therefore no, it is not inertial frame. The Earth as it rotates around the sun, yes. Now look at this. When I say Earth is rotating around the sun, it's an under circular motion. Circular motion is nothing but acted upon by a net force called centripetal force that results centripetal acceleration. Because there is acceleration, no matter if it is linear acceleration or centripetal acceleration, there is acceleration, then it is non-inertial frame of reference. So therefore there's only two options here which are inertial frame of reference. Okay, now I have a small question. Let's say there is a frame, I call it as S, and there is another frame of reference, it's prime. S is accelerating with acceleration A, and S prime is also accelerating with acceleration A. Basically, both are moving with the same acceleration A. Now, is S prime an inertial frame of reference with respect to frame S? You may think the answer is yes. I mean, yes, S prime is inertial frame with respect to S. So why? I mean, what could be the reason for you to answer yes? The reason could be that because they both are accelerating with acceleration A, that means S prime is at rest with respect to S. Similarly, S is at rest with respect to S prime because they both are accelerating with the same acceleration A. Now, so when I'm talking about S and S prime are accelerating with what with respect to what they're accelerating. So I have to include another frame. Let me call this frame A. Okay, a rest frame A. So S and S prime both are moving with respect to A with an acceleration A. That means S is non-inertial with respect to A, and S prime is not inertial with respect to A. But just now I said S prime is inertial with respect to S, and S was inertial with respect to S prime. I mean, same frames becoming inertial and becoming non-inertial while changing the frames. Now, that's not how the answer should change. Remember, when we talk about a frame to be an inertial frame, it is decided by, or it can simply be decided by, one of the particle within that frame. So for example, when I'm talking about S prime is accelerating with A, we know that all the particles within that frame is going to accelerate with A. If any one of the particle within the frame is accelerating, therefore the entire frame is accelerating, therefore that entire frame is non-inertial frame. But say, wait, are we not going to look with respect to something else? No, we're not going to look at when we talk about inertial frame or non-inertial frame, by looking at one of the given frame of reference, we're not going to answer that whether it is inertial or non-inertial with respect to any other frame. Instead, we're just going to look at just that one frame. Just look at this one frame and erase everything else from your mind. When we're talking about S prime is inertial or not inertial, just look at S prime and look at one of the particle within that S prime. If that one particle in that frame is accelerating, therefore the entire frame is accelerating and hence non-inertial. That's it. Similarly, when I'm talking about S, because one of the particle will be accelerating. Why? Because the entire frame is accelerating and hence S is also going to be considered as non-inertial. Now, because S prime is not accelerating with S, and S is not accelerating due to with respect to S prime. No, no, no. Don't compare like that. Don't look at relatively. When you answer about a frame to be inertial or non-inertial, we don't answer it relative to some other frame. Instead, it should be answered within that frame. Okay, I repeat my statement. When I'm talking about a given frame is inertial or non-inertial, to answer that, you just need to look at one of the particle within that frame. If that particle is accelerating, we say the entire frame is accelerating, hence non-inertial. If that one of the particle is not accelerating, that means the entire frame is not accelerating, hence non-inertial. Sorry, hence inertial. Okay, if that's clear, let's move on. So take this, one of the frame, I'm taking it as frame S. And there's a ball that fell down at a time period t. After t seconds, the ball falls at this position. So what is this position will be labeled as? Position will be labeled as x because x is nothing but with respect to this frame s, how far is this ball at a given time t? It is at a distance of x. Okay. Now, what if I'm going to take two frames this time? One is going to be my rest frame s, and one is going to be my moving frame s prime. So assuming that the moving frame is going to move with velocity v in the forward direction, and after time t, a ball falls down. So how far is this frame from the rest frame? Obviously, the answer is going to be v times t because speed is v, and I'm measuring this distance after time period t. So therefore, the distance is going to be speed into time, which is v times t. How far is the ball from the moving frame, which is s prime frame? It is going to be x prime. Okay, I repeat. How far is the ball from S prime frame? It is going to be x prime. And how far is this ball from S frame? It is going to be x. All the notations are very important. If you look at it, I repeat once again. These two are positions of the ball with respect to the two frames. Whereas this speed into time is the position of the S prime with respect to S. Okay, so when I'm talking about the object positions, we use the letter X. Now we use whether X prime or just X. It's based on with which frame we are looking at. I repeat once again. The position of the object, is always denoted with the letter X. So when I'm writing X or X prime, it depends on am I measuring the distance from the frame S or measuring the distance from the frame S prime. So again, going back, so x prime is the distance of the ball from the frame S prime, whereas x is the distance of the ball from the frame S, whereas v into t is the distance of the moving frame with respect to the stationary frame. Okay, if that's clear, that's clear. We'll do simple math to find the relationship between this x and x prime. So can I write the sum of Vt, the sum of Vt and x prime is equal to x? That's what I've written here. Vt plus x prime is x. That implies x prime will be x minus Vt, whereas t prime will be t itself. So what do you mean by t prime is t? So after how much time is the ball fell down with respect to the S prime, if I say 3 seconds, then obviously that ball has fell down after 3 seconds with respect to any other frame also, right? And these two equations that I've written are called as Galilean transformation equations. Okay. And these two formulas are there in your data booklet. Now moving forward, let's say there is a ball inside a train. I'm going to consider a moving frame as a train for easier understanding purpose, and the stationary frame S as Earth, okay, or the ground. So let's assume that the train is moving with a speed 40 meters per second, and inside the train, the ball is moving with a speed 20 meters per second with respect to the train. I repeat, the speed of the ball, which is 20 meters per second, is with respect to the train. That's why I wrote it as U prime. If I would have written the speed of the ball with respect to the ground, then I should have written with the letter U. If that notation is clear, let's move on. So because the ball and the train is moving, that's how after 2 seconds the position of the ball can be, and that's the position of the origin of the train. Now, how far the ball has traveled from the train origin or from the origin of the train. I'm considering this as origin of the train. So, right? So from the origin of the train, how far the ball has traveled. It has traveled a distance of 40 meters because the speed with respect to the train is 20 meters per second and the time is 2 seconds. So distance will be speed into time. So which is 20 meters per second into 2, which is 40 meters. How far the train has traveled from the ground, right? From the origin of the ground, how far the train has traveled. Answer is going to be obviously again speed into time, which is 40 meters per second multiplied by 2 seconds, which is 80 meters. But then how far is the ball from the ground? Answer is going to be 80 meters plus 40 meters, correct? Yes. So therefore, total distance is going to be 120 meters. And how long did the ball took to travel this 120 meters from the origin of the ground? Obviously, 2 seconds. If that's true, then what is the speed of that ball with respect to the ground? The answer is 60 meters per second. And you can see the 60 meters per second seems to be the addition of the speed of the train and the speed of the ball with respect to the train. And hence gives us a relationship that U is equals to V. Ignore that T here, sorry. If U is equals to V, which is speed of the train, plus U prime, which is speed of the ball with respect to the train, and hence I get another equation. So u prime is equals to u minus v. Ignore that t again. So u prime is equal to u minus v. So this is the third Galilean transformation equation for us. Clear? Next question here. A bird flies due south at 4 meters per second. So there's a bird that's flying south with a speed of 4 meters per second. Let me call that as velocity of the bird, VB. A glider flies due north. Okay, so the glider is flying due north. So glider speed is 5 meters per second. So they are basically with respect to the ground. The examiner will make it more clarity in the question, but let me tell you here that these speeds are with respect to the ground. So because they are the speeds with respect to the ground, it will change as per the standard notation that we have learned, like u, v, u prime, all that. Let's continue the question. What is the velocity of the bird relative to the glider? So question is, what is the velocity of the bird related to the glider? And glider is a moving frame, S prime. And ground is a stationary frame, S. So S prime in this question is your glider and S is your earth. So what is the speed of the glider with respect to the earth? Because that's the glider is a moving frame, no? So that's denoted with the letter V. Remember, V is nothing but speed of the moving frame with respect to the earth. So what is the speed of the glider with respect to the earth? It is V equals 5 meters per second. I'm assuming north as positive, north speed to be positive, then south will be negative. Then what is the bird speed with respect to the ground? It will be u only, no? So bird is the object here, like a football in our example, like football inside the train. Here, the bird is like a football inside the train. So what is the speed of the bird? Speed of the bird. So bird becomes object here. So u with respect to the ground is negative 4 meters per second because it is opposite towards south. So south will become negative. Now the question is, what is the velocity of the bird with respect to the glider, which is u prime? Yes. What is the velocity of the football with respect to the moving frame, u prime? So you have to find out u prime value. So what is the equation that we have got just now? So u prime is equal to u minus v. I'm going to write that equation. U prime is equal to u minus v. So what is u? U is minus 4 meters per second. Minus, what is the value of v? Minus 5 meters per second. So answer is minus negative 9 meters per second. So question answer is the velocity of the bird relative to the glider is 9 meters per second, and the direction will be towards south. So why towards south? Because we got the answer in negative, and we assume that south to be negative. Clear? Next, a ball rolls on the floor of a train at 2 meters per second, right? So this is the ball rolls on the floor. So it's a object speed. Now you have to see whether this is u or u prime. We don't know. If this speed is given with respect to the ground, we say u. If this speed is given with respect to the moving train, then we say u prime. So we'll continue reading the question. So ball rolls on the floor of a train at 2 meters per second towards right with respect to the floor. Floor means ground. Sorry, floor of a train means with respect to train it is. So this is your u prime. Now the train moves with respect to the ground to the right at speed of 12 meters per second, right? So if I assume this speed to be the positive, right as positive, then this speed should also be positive because this is also to the right. Now, what is it? The train moves with respect to the ground. So this is the speed. Train is your S prime. So speed of the moving frame, which is train here, is represented with the letter V, which is plus 12 meters per second. Now the question is, what is the velocity of the ball related to the ground? So ball related to the ground is nothing but u. You have to find out. So if u prime is u minus v, so u will be u prime plus v. U prime plus v. So u prime is 2 meters per second plus v is 12 meters per second. So answer is going to be 14 meters per second. Correct? Next. Obviously, positive means to the right. If you have to say, you can mention to the right. Now, what is the velocity of the ball with respect to the ground only? But this time, the train is moving to the left. So left will be minus 12 meters per second. So V is minus 12 meters per second. So again, the formula U is equal to U prime plus V. So U prime, it's the same value, positive 2 meters per second, where V is now minus 12 meters per second. Therefore, answer is negative 10 meters per second. That means the ball is moving to the left with a speed of 10 meters per second with respect to the ground. Okay. Now let's take another situation here. Say that S is going to be considered as ground for us, which is your stationary frame. And S prime is going to be, say, a train, which is going to move with a speed of 40 meters per second. And train has a flashlight in front of it, or light in front of it. And it's going to emit out the photon, right? There's a photon which is going to be emitted out. What is the speed with which the photon is going to travel? It is the speed with which it's the speed of light, which is 3 times 10 to the power of 8 meters per second. Now, let's say that after 2 seconds, the train reaches, the origin of the train reaches here, and the photon reaches there, right? That's the photon that has reached there. So what will be the relative speed? And what will be the speed of the photon with respect to the ground? Obviously, the speed of the photon with respect to the ground, u will be u prime plus v according to the formula, right? So what is u prime? It is the speed of the photon with respect to the train, which is 3 times 10 to the power of 8 meters per second. Plus, what is the speed of the train, which is 40 meters per second. So this says that the speed of the photon with respect to the ground is 300,456. I think, or maybe a zero wrong, we ignore it. This much meters per second. And which is not true, right? That's not true. That's not possible because the the maximum speed with which anything can move is the speed of light, and nothing can move beyond the speed of light. Even photon cannot move with the beyond speed beyond the speed of light. And that means this is not possible. And when I say this is not possible, that brings us a doubt that is Maxwell's theory wrong? What is Maxwell's theory of electromagnetism states? It states that the speed of light should be same for all inertial observers, right? Whereas Galileo's formula just now states that u is equal to u prime plus vt, which has given the speed more than the speed of light. This formula has given us the speed to be more than the speed of light. And if I assume that this is true, then I'm saying this is wrong. If I assume this is true, then I'm saying Galilean formula is wrong. And that's what Einstein has thought of. And he believed that Maxwell's theory of electromagnetism holds true. And therefore, he decided that we have to revisit the Galileo's relativity formulas, right? He has to revisit Galileo's relativity formulas. I mean, it was very clear that the Galileo's transformation equations, all those transformation equations were 100% correct when the object is moving with the speed closer to the speed of, sorry, and any object is moving with the lower speeds. But if the object or anything moving with the speed closer to the speed of light, as this example here, because the photon is moving with the speed closer to the speed of light, or basically equal to speed of light, for a faster moving objects like the photons, the Galilean relativity fails. That's what we have proven here. Then what should Einstein do now? So Einstein said, we have to revisit. We have to make some changes to the Galilean relativity formulas, Galilean transformation formulas, and then he finally came up with two popular postulates of special relativity. First one, which is pretty much same as the old one in a sense. First postulate of Newton or Galileo, but uh, as per the Galilean's postulate, that only Newton's laws of physics, only laws of mechanics are same in all inertial frame of reference. Only Newton's laws were obeyed, but Einstein said no. All the laws of physics, such as laws of electromagnetism, laws of optics, they all the same in all the inertial frame of reference. Basically, any frame of reference which is not accelerating, all laws of physics are simply applicable. You can apply. Go ahead, apply. They are they are applicable. Okay, that's first one, but little modification that instead of only laws of mechanics, that all laws of physics are applied in all inertial frame of reference. Whereas second one is new, given by Einstein, which says that the speed of light related to any observer in an inertial frame is independent of the motion of the source of light related to the inertial observer. Means that the speed of light is independent of the inertial frame, is independent of any frame of reference. It can be ground, it can be train, it can be aeroplane, no matter whatever is the frame you're talking about, the speed of light is independent. It is always constant value, which is 3 times 10 power of 8 meters per second. Okay. So he has given few equations called Lorentz equations. He has derived a similar equations on his own, but since these equations were previously derived by Lorentz, and that's why very popularly known as Lorentz equations. So on the left-hand side, you have Galilean equation for position and time, whereas on the right-hand side, you have Einstein equations for again position and time, whereas right, these equations are speed equation for higher speeds, right? Now, please make a note that all Galilean relativity is applicable for lower speeds, whereas Einstein relativity is applicable for any speeds, no matter whether it's low speed or high speeds. We'll talk about that situation later. That is Einstein equation applicable for lower speeds or not? The answer is going to be yes. We'll talk about it later. But look at the equation. What does it say? It says that the position or the time is not same for a moving observer and the stationary observer. It is different. And the different is given by a factor called gamma factor, which is given by the formula 1 over root over of 1 minus v square minus divided by c square. What is v? As I said very clearly, v is nothing but speed of that moving observer, speed of that moving frame of reference, which is nothing but speed of s prime, basically. Clear? And if I draw the graph between gamma and V over C, you understand that if V over C is equal to 1, the denominator value becomes 0 and 1 over 0 becomes undefined infinity. So that is why when the value of gamma is about, when the value of V over C is about 1, you can see that your gamma value goes infinity. There's a vertical asymptote at 1. What happens when V over C is 0? So when V over C is 0, the denominator value becomes 1. So 1 over 1 is 1, so gamma becomes 1. As you can see here, the gamma value is 1 when V over C value is 0. So if this it helps us understand that the value of gamma is from 1 and infinity. It always lies between 1 and infinity, including 1. Correct? I mean, what you understand is when the value of V is very, very, very small, right? When the value of V is very small, what happens? A very small value divided by a very large value, which is C square. So you understand this overall value gets negligible, which is about 0. In that case, the value of gamma becomes 1. And if the value of gamma becomes 1, substitute the value of gamma here 1, your x prime becomes the same equation as Galileo equation. Similarly, again substitute the value of gamma 1 over here, and V is about 0. This overall term becomes 0, so you end up getting the same equation as t prime is equals to t. So as I said very clearly that yes, Einstein equation is applicable for low speeds and high speeds, whereas Galilean relativity is only applicable for low speeds. Now, let's look at this question here that you are on an island watching the mainland some 20 kilometers away. The instant you see light from headlights of a car on the mainland, the clock strikes midnight. Okay, so this is mainland, and there's a car that shines the photon. There's a car that shines the photon. Okay, so you see after you are at about 20 kilometers far away from that, and you see the light reaching you at 12 o'clock midnight. So question is the time coordinate of the event light being emitted from the headlight is also 12 o'clock midnight? The answer is no, because the photon must have taken some time. It must have taken some time to travel this distance. Therefore, you have to subtract that time to talk about at what time this light or photon is being emitted, right? Next, lightning strikes a point onto the ground frame S at position X. So according to the frame S, lightning strikes somewhere, say at position X, which is equals to 3,500 meters, and time T. So at time T is equals to 5.0 second. Determine where and when lightning strikes according to a rocket that flies past the ground at speed of this much to the right. So there is a rocket. The rocket is flying. So V is equals to 0.80 C. So what is going to be, I mean, where? I mean, at what position from the rocket, which is called X prime, the lightning has occurred? And at what time, which is T prime, the lightning has occurred, right? So let's first find out X prime, right? So what is the formula for X prime, which is there in your data booklet, as you can see, X prime is equal to gamma times X minus VT. Clear? Now, gamma, which is, let's calculate that separately, which is 1 over root over of 1 minus V square over C square, which is 1 over root over of 1 minus zero point 0.8 C square over C square. So 0.8 square C square by C square gets cancelled. You're left with 1 over root over of minus 1 minus zero point 0.8 square. If you solve it, you're going to get 5 over 3. So let's plug in that gamma value over here. So that implies X prime is equal to 5 over 3 times 3,500 minus zero point 0.8 C times t, which is 4 seconds. Sorry, 5 seconds, right? Yeah, 5 seconds. Substituting the value of speed of light here will give you X prime as 2.0 times 10 power of 9 meters. Next, when? Then the question is when, which is you have to find out the value of t prime. So what is going to be the formula for t prime? You can look at the data booklet. T prime is equal to gamma times t minus Vx over c square. So gamma is already calculated 5 over 3. So t is your 5 seconds minus v is 0.80 c times x 3,500 divided by c square. If you simplify this, you get t prime as 8.3 seconds. Okay. So we'll do past paper question. One of the video I will make a video only on the past paper questions of the entire relativity. But right now, let's understand the uses of the formula first. Next, a rocket is moving at this speed. Therefore, the gamma will be 5 over 3. Just now we solved it. Where is the rocket according to the space station when the rocket clock shows 0.60 seconds? So this is the clock time on the rocket. So this is your t prime value, 0.60 microseconds. So where is the rocket? Means where is the rocket according to space station? So space station is your rest frame. Rocket is your moving frame. Clear? So let's say this is your space station and that's your rocket S prime. Okay. Now we're not talking about any object within the rocket. So if there was a football or anything inside the rocket, we would have written x prime to be some distance, right? Some distance of that object. But we're not talking about any object within the rocket, so x prime will be zero because there's no object inside. So x prime is zero. Because x prime is nothing but position of any object inside the rocket with respect to s prime. There's no object in this problem. Therefore, x prime is zero. B- And what will be x? X is nothing but basically the same distance the rocket has traveled. Okay. So what is the distance the rocket has traveled? It is speed into time. Okay. So question is, where is the rocket according to space station when the rocket clock shows 0.60 microsecond? So what's the formula for a rocket according to space station? You have to find a value of x. What is x formula? Gamma times x prime minus, sorry, plus vt prime. Now, as you know, x prime is zero. So x will be gamma times vt prime, right? And gamma is your 5 over 3. Vt prime is your 0.80c times t prime is 0.60 microseconds. So 10 power of 6 seconds. If you simplify this, you get the position as 240 meters. Now, what does the space station clock reach at this position, which is nothing but time with respect to the s, which is going to be t. So what is the formula for t? So t is equals to gamma times t prime plus vx prime over c square. So gamma is 5 over 3, so t prime is 0.60 microseconds plus v is given as 0.80c into x prime is 0 over c square. So this overall term gets 0. So your final answer t will be 5/3 times this value, 0.60 times 10 power of minus 6. What does this looks like? It looks like t is a gamma factor times t prime, no? Yeah. What does it mean? It means the time period or the time shows on the clock with respect to space station is larger than the time shows on the clock with respect to rocket. What does it mean? For example, there is a rocket. Okay, there's a rocket, and there's a clock inside the rocket. The clock starts ticking and ends here, and that time is say 2 seconds. But with respect to the ground, if say the rocket is moving at the speed of 0.80 c, so that gives us gamma factor to be 5 over 3. So with respect to the ground, how long is that time? So t prime, it is 2 seconds, which is t prime is nothing but time of the clock or the duration of the time in the clock with respect to the rocket. But what will be the duration of the time with respect to the Earth? It is going to be gamma factor times 2 seconds, which is going to be 5 by 3 times 2 seconds, which is going to be 10 over 3, which is 3.3 seconds. That means the person who is inside the rocket, for him, if the time spent is 2 seconds, during the same time, another person on Earth spends 3.3 seconds. That means the clock for the person inside the rocket is clicking or ticking slower, whereas the clock ticking on Earth faster. And that brings us a twin paradox given by Einstein. Let's say there are twins, okay? A and B are twins. So B left A from the Earth on a rocket when the age of A and B was 10 years. They both were 10 years old when they left. So B went on, spent 10 years in space. That means when he's coming back to meet A, he's 20 years old. But he will find, you'll be surprised to see A to B. If assume that he was traveling with a speed of zero point 0.8 c, then he will find that A is 5 third 20 years. That means 100 by 3. That means 33 years old. He will find his twin is 33 years older. So not 30 years older, 33 years old, which is 13 years older than him, right? And this effect of relativity is called as time dilation. Okay, this effect of relativity is called as time dilation. And if the speed increases, the value of gamma factor increases, that increases the value of time for the person on Earth even more. Maybe he will be 40 years old when he comes back if he is moving with a speed of 0.90 c. And this effect of relativity is called as time dilation. We'll talk about this time dilation and another effect called length contraction in the future slides. Let's move on. Okay, that's the time value which we have already discussed. Now, space-time interval. So what Einstein surprisingly found in his calculation that how a Pythagoras theorem talk about a length of a ladder. Let's say I'm asking you what is the length of the ladder, a ladder which is on the x-axis. You will say it is 10 meters in length. And if I'm rotating the ladder by an angle of 30 degrees, the length on the x-axis will no longer be 10 meters, maybe 8 meters. But you can still find the length of the ladder by knowing how much it is projected on the y-axis and how much it is projected on x-axis. And by using the Pythagoras theorem, which is x squared plus y square, gives you the length of the what? Ladder. So you understand that no matter how much you rotated the ladder, to whatever angle you rotated the ladder, by using Pythagoras theorem, you are able to find the actual length of the ladder. Similarly, it's not exactly, but it's an analogy that it looks like a Pythagoras theorem. You can see that some quantity square minus some quantity square, right? And what is that quantity square, quantity square? These are distance quantity. This is your distance quantity. It's a weight. How that is a distance quantity? C is nothing but speed of light and T is time period. Yes, it is distance quantity because you know distance is equal to speed into time. I'm talking about a photon is moving a speed of 3 times 10 power of 8 meters per second. How much distance will that photon travel in 1 second? Which is going to be 3 times 10 power of 8 meters per second multiplied by time 1 second. So it must have traveled a distance of 3.3 times 10 power of 8 meters. I've asked you how much distance the photon has traveled in 2 seconds, which would be 6 times 10 power of 8 meters. And how much distance the photon has traveled in time t seconds? Answer is going to be 3 times 10 power of 8 into t seconds, which is can be written as c times t. So c times t is basically the distance the light has traveled in terms of speed of light. So don't get confused. It looks weird, but yes. So this is the distance quantity in terms of speed of light. Okay. And this is also a distance quantity. Correct. So this distance quantity square minus this distance quantity square is called as invariant interval. This is your invariant interval. And what Einstein has said that invariant interval or space-time interval denoted with letter delta s square, which is c times t whole square minus delta x whole square. For this is with respect to frame which is at rest. What about a frame which is moving? So delta s prime square will be c times delta t prime square minus delta x prime square. So what Einstein has observed with his calculation that with respect to any frame, the time may not be same due to the time dilation. The length may not be same due to the length contraction. This is all due to the relativity effects, but something that is always equal, something that can always be determined, they're equal, which is space-time interval. And that is your delta s square is equal to delta s prime square. And that gives us this equation for us or expression for us that ct square minus delta x square is equal to ct prime square minus delta x prime square. But why are we learning this here? The reason we're learning is to understand that when we solve numericals, let's say your time period with respect to Earth is given, the change in position with respect to Earth is given, change in position of the object with respect to moving frame is given, and asking you what is the time period with respect to the moving frame. You can use this equation instead of using Lorentz transformation. What is the advantage? Nothing, just that you can skip that gamma factor because this equation doesn't need a gamma factor. But again, as your convenience, if you're comfortable with Lorentz, you can go ahead and do that. If you're comfortable with space-time interval, you can go ahead and do this, right? So if you still have a confusion, let's do a problem. I'm going to solve this question by using both Lorentz transformation and using space-time interval. So consider an observer X at the origin of frame S prime. Okay, so there is an, let me erase the board, give me a minute. Yeah, so consider an observer, there is an observer X where at the origin of S prime, which is a moving frame, that moves past a frame S with a speed 0.80 c. So what is the speed with which this frame is moving? 0.80 c. What is the speed with which this observer X is moving? Also 0.80 c only, right? Because it's not moving with different speed. It is always at origin. So while origin is moving at 0.80 c, the x is also moving at the same speed, 0.80 c. An observer in S measure that x turns on a light at time t equals 0 and turn it off at time 4 seconds. So there is an observer S. Let me call an observer S at origin again. Let me call that observer as A. So what he observed is that the torch light is turned on at time t equals 0 and torch light is turned off when time t is equals to 4 seconds, right? So while turning on and turning off, the frame has moved a certain distance. What will be the formula for that? It is going to be V times the time duration, which is 4 seconds. So V is 0.80 C times 4, right? So you get the value of how far the moving frame has moved. Now, for how long was the light on according to S prime? So the question is, if the time duration with respect to the ground delta t is 4 seconds, what is the duration of the time with respect to S prime, which is delta t prime is what they're asking us to calculate. So first what we'll do is we'll use the Lorentz transformation equation to calculate the value of delta t prime. So what is delta t prime? So delta t prime will be gamma times delta t minus v delta x over c square. Now don't get confused. You have the formula t prime is equal to gamma times t minus vx over c square. From there only we have written the formula for delta t. That's it. It's just change in time or time. The formula looks pretty similar. Okay, so you don't need to think too much about it. If you're writing in terms of time, just write t. If you're writing in terms of time period, time duration, change in position, instead of x, you'll write delta x. That's all the differences, right? So do we know the value of gamma? Yes, because the speed is with which it is moving at 0.80 c. If you calculate it, you will get gamma to be 5 third. So 5 by 3, sorry, 5 by 3. What is the duration? Delta t, 4 seconds minus v, 0.80 c. What is the change in x? Which is nothing but what is the change in position of that observer x with respect to the stationary? So change in distance will be obviously speed into time, which is 0.80 c into 4 seconds. So you'll substitute there 0.80 c times 4 seconds divided by c square. This c and c square from the denominator gets cancelled. If you simplify this, you're going to get t prime, change in time period with respect to s prime is 2.4 seconds. Clear? Very simple. But remember, I use Lorentz transformation. This time I'm going to use space-time interval. So what is space-time interval? It says that the delta s square is equal to delta s prime square, right? So what is delta s square? C times delta t whole square minus delta x whole square is equal to c times t prime whole square minus delta x prime whole square. Now, since delta x prime is 0, why? Because as I said, the observer x is not moving anywhere with respect to the s prime. It is at origin always. It's not, there's no change in position. But its position is changing with respect to the S frame. I repeat, with respect to S frame, the position of X is changing, right? Because S prime, because the S prime is moving with speed V. So X was here initially and later it is here. So with respect to this stationary frame S, the position of X is changing. So that delta X can be calculated by speed into time formula. Whereas the X position delta X prime with respect to S prime is not changing because it was here and it stays at origin only. There's no change in position. It's staying there only. It's not moving. So delta X prime is 0. So substituting that, I mean delta X prime 0 will make, so substitute the value of C, delta T is 4 second, delta X can be replaced with what? Speed into change in time, right? So substitute there. C is substituted, delta t prime is what you have to calculate. If you simplify it, you again going to get 2.4 seconds. Okay, so something that is very important from this problem you have to learn is one, that why is delta x prime 0 in this question is because the observer is not moving, right? The observer is not moving with respect to S prime. The observer X is moving only with respect to the frame S. So delta X is zero, delta X dash is zero, but delta X is not zero. How much is it? V times T. Second thing to be noted down here is that, yeah, the delta X is equal to V times T. Why I'm doing this? Because the change in position of X is the same change in position of the S prime. If S prime has traveled the distance of V into T, the observer X has also traveled the distance V into T only. They both are the same. Okay. Now, a photon travels from A to B on a straight line. What is the space-time interval for these points? Which points? A and B. So point A is here, point B is here. So say the photon is emitted at point A and reaches point B by total in a time period of delta t by traveling a distance of delta x. And what is the speed with which the photon is traveling? It's c. Now, what is the space-time interval, right? The formula is c times delta t whole square minus delta x whole square. So question is, what is the value of this space-time interval? What is the value? So what is the distance traveled? The distance traveled by photon will be the speed of the photon multiplied by the duration of the photon, how far, how long it traveled. Speed of the photon is c, and it traveled for a duration of delta t. That's what I mentioned here. So when I substitute that, so c times delta t whole square as per the formula, in place of delta x, I'm replacing with c times delta t whole square. So they cancel out each other. The space-time interval for the photon traveling from A to B or anywhere is zero. Yep. So in the next class, we'll talk about effects of relativity. That's it for today.